Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Welcome to another very engaging Australian Water School webinar. We can't wait to get into this. And today, we're going to be talking about energy losses at structures with an outstanding team from TUFLOW. Presented will be Bill Syme and the panelists Chris Huxley, Schwangau and Phil Ryan. The number of people at this webinar is fantastic. Spread across the world, a lot of people have a lot of interest in the topic, and we're so glad you've joined us. Well, let's get into this. Bill has over 30 years experience in flood hydraulics field. TUFLOW software was developed by Bill, starting back in the rocking and rolling 1989. Wow, it's not the 60s and 70s, but it's way back. That's good, Bill. And Bill is a software business lead managing TUFLOW products and associated services. Welcome, Bill. How are you today?
Good, thanks, Trevor.
You got a lot to say, so we won't muck around with too many details. But we did appreciate everyone before the webinar started answering a small poll. There we go. Commercial consulting way out in front. Sort of what we expected, right?
Yes, as expected. This is the interesting one. So your most common approach to modeling hydraulic structures. Yeah, so gee, neck and neck on the first three.
It is.
Yeah, very interesting. Yeah.
That'll be some Q&A time later in the webinar.
This presentation's for the focusing on the first three, so that's great.
Thank you so much, everybody. It gives Bill an idea who he's talking to, and I think that's probably all we need to say at the front end here. What do you say, Bill?
Into it.
Crank into it. Let's go. Let's do it. I'm looking forward to this.
Okay. Today is all about modeling energy losses at structures. So let's get into it. Today's focus is going to be very much about the cross drainage structures, such as one in the video there. So we're talking about bridges and culverts, and basically anything that takes flow through an embankment is really the focus of today's discussion, but it could apply to any sort of structure over an open channel, basically. We are going to cover other sort of related topics, such as pipe networks in a webinar next year, February 16th, and operational structures will be in a webinar on April 13th, 2022. So keep those in the diary. They'll be good ones to attend if you have an interest in those spaces. So today's agenda, well, we can't escape this with a little bit of theory, so I'm going to dive in and give you my take on how to interpret what energy or form losses are and how they influence things. I'm then going to just briefly cover the different ways you can model a hydraulic structure, 1D, 2D, 3D, just give an overview on the options there. And then we'll focus on a series of benchmarking tests just to demonstrate how different approaches can affect your results and try and give some insight as to maybe the best way to model a hydraulic structure, a cross drainage structure. So I'm going to really focus on what happens at constrictions, what happens around piers, and what happens when your bridge deck gets surcharged or submerged. Of interest to me, of course, is I first presented this topic on 2D modeling of bends and hydraulic structures in 2001, so nearly 20 years in November ago. So I'm feeling quite old, but it's something that's, whenever I give this presentation in a training course or something like this, or a related presentation, it always it gets attention. So let's see how we go. For those who want to read the paper, the link's down the bottom. So what are form losses? It's pretty important to understand. It's a term we use a lot in our TUFLOW documents. What is actually a form loss? So when you have water moving along, such as in the video there, basically the energy of that flowing water has been dissipated principally as heat, but that's coming from a friction against the bed surface. So we all be very familiar with the Manning's equation. It's one of the most common equation used to represent that bed resistance. But there's also quite a lot of energy being dissipated in this situation on the video there, just due to a change in the flow formation. So wherever water is forced to change direction or it slows down, it loses its energy. And that's really what we're talking about today. So, and you have a change in that flow formation, change in your streamlines, such as at bends and constrictions. You have this loss of energy, and we refer to that loss of energy as form losses. So to understand form losses, you have to dive into your textbooks and just think about what the energy of water is made up to. And in its simplest form, it's basically your water surface plus your V squared on 2G is your total energy. So when in a lake where the water is not moving, your total energy actually is the same as your water surface because your velocity is 0. But as water speeds up, you start to see a dip or a drawdown. And this nice little image on the right demonstrates it quite well. So if we were to draw a line along the water surface there, it would look something like that. But the total energy will be pretty constant. It hasn't, at that point, the water hasn't really lost any energy. But what's happening here is that as the water speeds up, as your V velocity increases, it generates a kinetic energy. And so your water surface has to drop to compensate for that. So basically, wherever water slows down, the V squared and 2G reduces and the water level flattens or rises, and you'll have the water surface will be very similar to your total energy. But as water speeds up, the V squared and 2G increases quite markedly, and your water level surface drops. So that's really important to appreciate that, because that's really what form losses are all about. It's basically a loss of that kinetic energy. And it's important to keep V squared and 2G in your mind, because that squared, the velocity squared, is the killer. So if your water is only moving 1 meter per second, your kinetic energy is actually only about 5 centimeters. It's not an awful lot of energy to lose there. But if your velocity is ripping along at 4 meters per second, as many faster flowing rivers will be flowing at, you're getting close to 1 meter of kinetic energy to be lost. So that's a lot of force, a lot of energy to be lost. And so when we talk about a form loss coefficient, we're talking about a proportion, a coefficient that sits in front of the V squared on 2G, which represents the amount of kinetic energy that is lost. So I'll refer to form loss coefficients quite a lot through this presentation. So let's try and understand how form losses are modeled. This slide is actually from my 2001 presentation. So it's a little bit old, a bit outdated. But what we have here is a very simple 1D model. And because it's 1D, it actually has no knowledge that there's a bend there. That equally could go to the right, or go straight ahead. And if you run that model with a steady flow, in this case, a velocity of 2 meters per second, you basically get something that follows the Manning's equation. So it's just bed friction that's following this red line down the middle here. To make a little 2D model of that same setup, you get some nice little flow patterns around the bend. You get a surcharge of water level here as the water tries to super elevation around the bend that pushes up against this side. It's much more interesting, much more exciting. And if you plot the profile, you'll end up with something like that. So, and the total energy would actually sit above all this, of course. The energy doesn't really drop until it quickly until it goes past the bend there. So what you're seeing here is the 1D model doesn't model the form losses at a bend because it doesn't know it's there. But the full 2D equations can model a bit, the form losses around a bend, and consequently, you need a higher water level on the upstream side to push the water through. So that's why you see basically a higher water level coming out of the 2D model, because it needs more energy to push it around that bend. Now, clearly, the 2D one will be closer to the right answer than the 1D in this case. And how do we sort of know what to put into a 1D? Well, because they don't simulate form losses, we need to apply a formal bend loss. And as I said, 2D equations, they just simulate the form losses, but they don't simulate all form losses, such as those in the vertical. And if we had the luxury of being able to run 3D models, you'd be closer again. I'll talk about those a little bit more later on. What's really important to understand is that you cannot use the same form loss or same energy loss coefficients between 1D, 2D, and 3D. It's not like Manning's N, where the Manning's N is generally transferable between 1D and 2D, but you cannot transfer form loss or bend loss coefficients. And the Brisbane River flood study, which is one of the most exhaustive flood calibrations I've seen, is a good example. So there are numerous bends where we have really good calibration data. We had a 1D only model, and typically we needed a form loss or bend loss of 0.5 to 1.5, depending on how severe the bend was. But 2D needed much smaller values. And that's really because it picks up most of the bend losses due to its equations. It just misses out on some, such as in the vertical. But that's a very nice example how you cannot transfer one bend losses from 1D to 2D. Both those models did use the same mappings. The only thing different was the form loss coefficients at bends. So how do we go about modeling hydraulic structures? Let's look at 1D to start with. Let's go back to basics. And interestingly enough, 1D is probably the easiest way of all. And that's why a lot of people are probably still modeling structures in 1D. Effectively, with 1D, as I've been talking about, the velocities are unidirectional. It doesn't know anything about water bending and so forth. So you have to explicitly specify any energy lost, such as an entrance coefficient, which you'd all be familiar with, or an exit coefficient. So, you've all punched into your software what the culvert entrance loss coefficient is and what the culvert exit loss coefficient is. And the head drop due to those change in form is simply that equation there. The sum of the two coefficients plus the velocity of the structure squared on 2g. So that's pretty straightforward. It's very common. No dramas there. There's a lot of documentation around good values for entrance and exit losses. But what's probably not so well appreciated, you do need to adjust your loss coefficients with height. And not all 1D schemes do this. So for example, let's take the situation where we have a bridge structure over a trapezoidal channel. Up until this point here, the bridge structure doesn't impede the flow whatsoever. So basically there's no change in velocity through here. The water just carries on its way as if the bridge structure wasn't there at all. So effectively, there's no change in velocity. There are no form losses up until that water level here. But as the water level rises, the bridge starts to constrict the flow. And then the velocity in the structure starts to get greater than the approach or departure velocities. You'll start to see some eddies form on the downstream side. And suddenly we have a situation where there is a change in velocity, and therefore there will be losses. And so we need to simulate those losses. And the severity of those losses would vary with height. So I won't get too technical because I've got a lot of slides to present, but basically the equations that are used and documented quite a lot of places, as shown on the screen there. So the first equation is the entrance loss adjustment, and that's largely based on empirical testing. The second equation is actually derived from theory, so that one's, if you like, exact. There are plenty of published values for these K entrance and K exit. There's some on the right there for the entrance coefficient from the Queensland Urban Drainage Manual. And typically the values that people stick in are here. For the exit, you pretty well run with 1 the whole time because it's a theoretically derived equation. For entrance, use 0.5 if in doubt. You've all probably been there, or model 1D. What's really important is that we're doing this adjustment. So, and there's the equation as I've shown before. So let's return to our little example of the bridge over trapezoidal channel. So up until here, there's no change in velocities. And if you punch that into those equations, your adjusted K entrance and exit values come down to 0, and your head drop due to the structure is 0, ignoring any Manning's friction or that type of thing. Let's look at the case where the water level has risen, the bridge is starting to impose on the flow, we've got a change in velocity, say those numbers on the screen, and you can do the calc. So basically, your entrance coefficient has gone from 0.5 down to 0.12, and your exit from 1 down to 0.04. And so your head drop will be around 0.05 of a meter. So that's what should be happening behind the scenes in a good 1D scheme. Let's move on to 2D approaches. So 2D looks impressive. Always creates nice images. And this is one of the very first ones from TUFLOW from 1999, believe it or not. But is it accurate? You know, it's nice images doesn't necessarily mean that something's right. So as I've discussed, you know, 2D will implicitly model the form losses, and many people ask that question. The answer is yes, it does, but it can't model all of them. It doesn't account for subcell form losses such as Piers and vena contracta, and anything in the 3D, of course, the 2D scheme is, will represent not at all or very roughly. And so those missing form losses, how do we account for those? That is indeed a very good question, and that's what we'll be discussing. So here we have the 2D version of our little constriction. Water's coming through, speeds up and then expands, eddies form. So as we've discussed, it's not applicable to apply your 1D form losses. You know, otherwise, if you just applied your 1D form losses, yeah, you will be duplicating losses because the 2D is already knocking out quite a lot of loss in that system due to the more advanced equations. So our options are to just put a little bit of small form loss into there if we need it, or use a finer mesh, which is often not practical. And for that, that's really because if, for example, the vena contracta, the entrance losses are all about the vena contracta expanding. So the entrance loss is really occurring through this space here as the water expands and this eddy forms. And the sharper the edge here, the larger the eddy here, and the tighter the vena contracta, so the greater the velocity. So to model that, you would need a very, very fine 2D mesh. And that's just nearly, most of the time, it's not practical. There are other considerations as well. A good turbulence model is pretty critical as well in your 2D scheme, and you're getting down to this sort of level of modeling. So we'll touch more on the 2D in our examples, but yeah, that's the basis of where we have to go. We really have to either apply additional small losses or use a nice fine mesh, or maybe a bit of both. Now, the other arrangement is actually a 2D, 1D, 2D approach. So we actually replace this part here with 1D, and so I'll end up with something like that. Can we apply the 1D form losses just onto that 1D channel? No, that is a very emphatic no, because the 2D is still modeling some exit losses here. So you'll be just duplicating your losses. So yeah, you've got to be very careful when you insert 1D into 2D. So it's not correct to apply all 1D form losses. So tread carefully, and we'll have a look at that in some of the slides that are coming. I'll just touch briefly on 3D approaches. These are, if you like, the emerging ones. We're getting pretty excited with TUFLOW FV. We've actually just been building in some nice features. I won't go too much through all the functionality, but basically it's these layered 2D models, or we just call them 3D, but they're not CFD. They have several layers, and they have various viscosity models to allow that mixing in horizontal, but they also have a turbulence model for the vertical. So you can get 3D circulations generated, such as in that bottom image down the bottom. They still have the hydrostatic assumption. So that's why it differs from a CFD, or one of the main things that differ. We very much see these layer 2D models, which run much faster than CFD models, in the next sort of phase of hydraulic structure modeling. And we're putting some nice functionality into TUFLOW FV to do that. So watch this space. The other approach is, particularly if your model can be just confined to the structure itself and you don't have long simulation times in terms of hours or days, is to go to CFD. And effectively, now you're getting into the full Navier-Stokes equations. There's no hydrostatic assumption. You have a air-water interface. Yeah, I'm not a CFD expert, but it's pretty full on. So this is as full on as it gets. But consequently, yeah, there are downsides. You need a very high resolution mesh to actually represent the structure in detail. But what you don't need to do is any submodeling of blockage factors or form loss coefficients, in theory. So yeah. A really good eddy viscosity model is critical while the flow is non-laminar, which is pretty well all our situations. The big downside, very long simulation times and not yet practical for real-world flood study investigations, but it can be very useful for individual structures. And of course, I should mention physical modeling, and I'll let you read that phrase on the screen there. But this physical model was the only one I've had anything to do with. I'm not a physical modeler, but this site we actually modeled in as a physical model, but also in 3 different 2D models and 4 different 1D models, including TUFLOW for the 2D and the 1D. And I guess if it wasn't for this study, I wouldn't be here talking to you today. It really made or really demonstrated what TUFLOW could do, which is very rewarding but full-on study. But the one thing I did learn is this phrase. It's quite interesting to talk and watch the physical modelers. Anyways, let's move into some examples. So we're going to first talk about constrictions. So to demonstrate flow through a constriction, we've just set up this little test model. It's 30 meters wide, 1,000 meters long. And in the middle here, we've got a little 10 meter wide, 10 meter long constriction, which we're modeling it as a sort of effectively a culvert that's not surcharging. There's some details there on the model there if you would like to reproduce it. So let's first look at a 1D, 1D, 1D. It's a pure 1D model of that arrangement. So there's the model results there. You've got this is the culvert. This is the upstream water level. You can see there's afflux. This is the red dashed line is without the culvert, without the constriction. So you see there's around about a 0.3 meter afflux there. In fact, the exact number, if you want to pull it out, is 276 millimeters from this little TUFLOW model. And and something that's really worthwhile doing, we're just modeling it as a square edge, so entrance loss of 0.5. You can also do a desktop calculation, and your adjusted entrance loss comes down from 0.5 to 0.36, and the adjusted exit goes down to 0.48. That gives a form loss of about 250 millimeters. There's also a bit more bed friction through here because the water's moving faster through the culvert. We've kept the same Manning's end through the whole, both culvert and open channel, just to keep it simple. Anyway, so the afflux from a desktop calculation is about 271 millimeters, which agrees very well with the 276. So that's a nice little test. It's always worthwhile doing those little desktop cross checks. So that's the case that comes out of the little 1D model, and that's adjusting the losses. What happens if we fix those losses at 0.5 and 1? So the end result is that the afflux is over-predicted, as you can see here. So this is the upstream water level if you don't adjust the losses. And you will, according to theory, over-predict your head drop above that constriction. Effectively, this situation here is if the water is going from a still water situation to a still water situation. So effectively from a lake to another lake, where your velocities and two water bodies are 0. What's important to realize is that most published K values are usually based on the unadjusted situation. So just keep that in mind when you're taking values from the literature. Let's make a little 2D only model now, exactly the same setup. So we'll step through some different cell sizes. There's a 10 meter grid, only 3 cells across here, 1 cell through the constriction, pretty rough. There's the results. And you see the legend on the right, we've got water level being shaded here. And as this gets, you'll notice here, as we go to a finer grid, that this color here gets more red. And basically, as you go finer and finer with your 2D cell size, your afflux increases. There's a 2.5 meter. And at 2.5 meters, we're starting to see some nice resolution of an eddy, and basically starting to model the form losses through the system. There's 1 meter, so we're starting to really get into nice detail, but it's getting much redder, so the afflux is going up. And there's 0.5 meter, so dense you can't even see the arrows. But if we plot up the profile through here, through down the middle here, from those different cell sizes, this is what we have. So there's the dark blue line is your 1D profile. There's the 0.3 meter, 0.27 meter head drop. The 2D, so the bottom ones here are the coarser ones, and the finer ones, top ones are the finer mesh ones. So from 10 meters through to ½ meter here. It's quite interesting because what you're seeing is that you tend to see the coarse mesh results converge together down here. Then we go through this transition period, in this case around 2.5 meter cell size. And then the finer mesh results converge up here. So it's almost, we've got two sort of convergence points. And that's because we're going from a situation of these coarse models not being able to model those form losses very well because they're so coarse, heading up to finer mesh results, which are modeling those form losses quite well and producing a greater head drop. So interesting. What you've also noticed is that the fine mesh ones are sort of producing a higher level than the theoretical solution. So now that can be dealt with reasonably easily. In this case, it's all about the subgrid turbulence representation. We've brought that down to a Wu value of 4. 7 is the default in TUFLOW for most real-world studies. But we found during our testing on the Wu that we sort of from a value from 3 to 7 was pretty good. Most models fell in that range. And so if you change it to 4, you'll start to see you get the right head drop for those fine mesh models. So the rest of the benchmarking I'll show is using a Wu turbulence of 4, just so we're sort of staying consistent with what the theory would tell us. What's interesting is you can sort of attribute about 0.2 of a meter of the head drop to the pressure forces of the walls against the, and about 0.1 to turbulence. So it just does highlight the importance of having a good turbulence scheme in there. Just out of interest, we ran the model in first order. So TUFLOW HPC has both the second order, which is the default, and first order option. And typically it did what we expected and produced a slightly higher head drop. First order schemes tend to be a bit numerically diffusive, causing artificial energy losses. So to get the first order scheme working, you'd have to drop the turbulence coefficient further or possibly reduce Manning's N is another way of dealing with that problem. Not ideal though. You can see both schemes are sort of converging there. This is the number of cells across the culvert. This is the head loss. So this is your second order at the bottom and first order there. It does highlight the importance of making sure you know two different schemes will give you exactly the same results. So you do need to understand and test your scheme. So how do we deal with the fact that these coarse meshes, so in this case here, a 5 meter grid, this coarse mesh doesn't reduce enough form losses? You know, it's sort of sat in that sort of gray in the lower space below down here. So really the only option is to apply another additional form loss. So in this case, if we put an additional form loss on these cells here of 0.36 times V squared on 2G, we push up the upstream level from this point up to here, and we actually match very nicely what you get with the very fine mesh results. Also matching much more nicely with the 1D theoretical result. And of course, what was quite interesting is that little exercise is that the entrance loss is actually 0.36 in the theoretical solution. So yeah, it's a nice sort of match there, but it will be cell size dependent, which is where we struggle. And of course, with fixed grids, that's less of an issue with flexible meshes, of course, but your 2D cells may not align very well with the actual opening. So here we have a 7.5 meter mesh and a 1.5 meter mesh. I also modeled a 3.75, and you see they're all over the place. So you know, you're not getting a good reproduction of the afflux. This is the afflux along here at these cell sizes which don't match the opening exactly. But we do have a bit of a solution, or quite a nice solution for that. If you turn subgrid sampling on in TUFLOW, that helps enormously, and you get a much closer match to what a nice fixed cell size that fits in there perfectly. So it's not exactly there, but it's giving a much better result. So if you are modeling any of these structures, make sure you have your subgrid sampling on. Now let's look at putting a 1D element in there. So we basically isolated those 2D cells, put in a 1D element and connected that. And we're just using this most common way in TUFLOW is using the SX link. So the water comes in and through the 1D column and gets spat out the other side. It doesn't necessarily produce great patterns downstream, but it gets the water through the embankment. So what happens when you do that? And we just put the standard entrance exit losses, and they're unadjusted, the 0.5 and 1. And as we would expect, there's an overprediction of the afflux. And it's a bit to do with duplication of losses, and that 0.5 and 1.0 are just, we're just taking too much energy out of the system. That means we need a much higher water level upstream. So what can we do about that? Let's try putting the 0.36, 0.48 losses on this 1D culvert. So there's no automatic adjustment of losses here because this 1D structure is not connected to a 1D approach departure velocities. It's just connected into a 2D. When we do that, if you just put the 0.36 to 0.48, we come down a long way, so down to this green line, so much closer to where we want to be. And in fact, if we make the exit loss around 0.3, we actually get quite a nice match to the head drops through the structure. So that's all well and good, but the problem is that these numbers here will vary according to your cell size, because a finer one will need much smaller or none of these values, because a finer mesh, because it's modeling losses a bit better. It is going to be a little bit cell size dependent, which is not ideal. So a new feature we're building into TUFLOW is to actually take, and we've got a bit of a trial going already. You take the 2D approach velocity, take your 2D departure velocity, you then adjust these losses through here automatically, and you have to take the velocity well away from, away from the sort of change where the velocity is changing a lot. So you have to get upstream and downstream, which is part of the trick of doing this. So when we do that, we move the head loss from the orange line down to the green line, and this is just happening automatically. So you don't have to go in and worry about what form losses you're putting on there. So lots of things to think about when modeling a constriction. And but hopefully, particularly with this last feature, when that's fully implemented, which will be in the next version of TUFLOW, we will hopefully pretty well remove any sort of manual need to input or adjust losses. It will all be automatic, which would be very nice. Now let's move on to Piers. Now I'm going to first cover Piers with a fine mesh, but before I do that, Piers are also another form of constriction. They actually squeeze the water between the piers, which sort of saying the obvious, I guess. And what tends to happen is, there's your upstream energy level. You can always get a good idea from a pier where the upstream energy level is, because it's pretty close to where the water is surcharging at the top of that bow wave there. And then your downstream energy, so this is a pretty good indicator, because this is where the water's nice and still. Well, it's a little bit turbulent, but nothing like out here in the main part of the channel. So there's your drop in energy from the dashed line down to the solid line there. Now, the 1D approach to modeling a pier is pretty straightforward. It's just, most people have done this. You get your KP value from hydroxyl-rich waterways or some other source, and you simply apply a energy or form loss to that bridge structure. But if you move into 2D, in 2D world, you've really got two options. One is to just make a really fine mesh. And that's great if you can do that. We'll have a look at that. But the other approach is to obviously use form losses. Often your mesh, you cannot make your mesh fine enough to represent piers. So if you're applying form losses, there's been a lot of questions around that. And that's really, do you apply it across the whole waterway? Can you apply it cell by cell, directly where the piers are. Yeah, lots of questions. And I'll talk about those in a while. Let's look at the fine mesh situation. So we've been doing some more benchmarking around Piers, and this is a little flume test that was done in 2005. Pretty tiny, it's only 20 centimeters wide, so it's a very small little model. It's got a square pier in the middle, 4 centimeters by 4 centimeters, and details on the left there. There's two gauges which will show some results from. Gauge 1 is here, which is in line with the center of the pier, and gauge 2 is offset. So turbulence eddy patterns shown down the bottom right. So basically, what we've done is we've taken a fine mesh, start with the fine mesh, cell size 4 millimeters. So we've got about 10 elements across the pier. And we've run the turbulence parameter value from 0.2 to 7. 0.2 is actually the value used by the researcher in the paper for their modeling. As you can see, if you use this simulation animation is from the 0.2, it's pretty wild. So let's look at some results. So top image there is from 0.2. This is from 1. With value of 1 and then with value of 7. So you can see as you increase that value, it basically suppresses the severity of those vortices and of how the wake forms and goes. So if you want to really pick up what some turbulence and stuff going on downstream, you really need to have a value quite small. But if you're happy with just not having those, you can always have a much higher turbulence parameter. But what does that do to the results? Now, very interestingly, all those simulations produced a very similar afflux. This is on the upstream side. These squares are the measured values. So they all came in and gave a pretty nice match to what was actually measured. But they all gave a fairly similar afflux. It's only on the downstream side that you start to see some variation. And these are on the right is time history. So these lines on the left here, these are like an average of the time history at those gauges, well, on that longitudinal profile. So you can see here gauge 1. So if you have a low turbulence parameter, and this is at gauge 2, this is the velocity being plotted up over time. You see the measured values up here, and this is what's coming out of the model. So you see the periodicity is pretty similar to what was measured actually, which is quite nice. The amplitude differs quite a bit, so that's of interest. And you can see by the time you get down to a Wu parameter of 7, it's suppressing that circulations, and your simulation is truly steady state. It's not changing, whereas these ones here are steady state inflow, but a dynamic sort of reaction below the pier. So interesting outcomes there. Let's look at cell size results convergence testing. So we've gone, this is 0.2 Wu parameter, 7 Wu parameter on the right. We've gone from a 0.4 centimeter cell size to 2 centimeters. So by the time you get to 2 centimeters, you've just got 2 cells across the pier. The darker the blue here, the greater the afflux. So you can see as you increase your cell size, your afflux starts to decrease a bit. Not so much with the Wu value of 7. We look at some of the profile. So this is for the different cell sizes. The solid lines are for a Wu parameter of 0.2, and the dashed lines are for a Wu parameter of 7. So once again, we're seeing reasonably good similarity for the afflux upstream, which is very encouraging in the sense that if your focus is the afflux, you don't need to worry too much about your cell size at these resolutions or your turbulence parameter. But if you really want to pick up what's happening downstream, you do need to probably focus on varying that turbulence parameter. So unfortunately, not all piers are nice and square like that, which suit a fixed grid mod like TUFLOW HPC. So what happens with a circular pier? Now, unfortunately, they didn't put a circular pier into that little flume test, but we just replaced it with this and to have a look at what happened. So at the top is the square pier streamlines that are forming for HPC, which is a fixed grid, and FV, which is a flexible mesh. But on this top one here, we've actually modeled that with a regular mesh. So it's actually the same as HPC. So it gives a bit bigger wake, and the reason for that would be just the difference. So they are different solvers, so they are giving slightly different responses downstream. If we move to a circular pier using a fixed grid, you can see get quite a strong wake there, not as big as with a square pier, which would make sense. And this is FV on a regular fixed grid as well. And you see it's, once again, a bit bigger formulation, eddy form, but smaller than the square pier, but a bit bigger than HVCs, once again, due to the different solvers. If we move to turning SGS on for HVC, we actually do see a nicer response here. So you see here a much less eddies forming behind. So that gives what we believe a much more improved representation of the pier. And if you use FES with a truly flexible mesh, you get a very nice sort of streamline response around the back here. So let's look at some of the profiles. So on the left is HPC, the fixed grid, FV with its both regular grid runs and its flexible mesh in the green dash line. So the blue is a square pier, and that should match the measured values there. The dash lines are for circular pier, so we would expect them to sit below, have a lower afflux than the square pier, which both models are showing. And if we don't have it in the slide, but we did a bit of comparison with drag coefficients, and certainly FV is giving a really nice match with the smaller drag coefficient that you would have for a circular pier compared to a square pier. HVC with its fixed grid does reasonably well, but it doesn't pull it down far enough. So that green dash line with a flexible mesh and FV was on the money in terms of the drag coefficient comparison. Okay, so that's modeling piers with a fine mesh. Lots of interesting results there. And basically the outcome is you can do it. Piers using form losses. So the challenge we normally have is that often the pier sits inside the cell or is only covered by a couple of cells. So I'm just going to run through a little case study about how we go about doing that, some options. We can't always make the fine mesh we'd probably like to make. And one question we get asked a lot is, should we reduce the cell flow area by the pier area when applying these hydrology bridge waterway losses? So I'm going to answer that one first. So look, the answer to that is basically the hydrology bridge waterways actually states that if the piers are present in the constriction, these are ignored in the determination of the area, and that would then affect the velocity as well. So effectively, for hydrology bridge waterways, KP assumes that the area of the piers is not taken out of the model, out of the flow area of this 2D cells, or the 1D representation. So you should not apply blockages from piers. That's what it would imply. So anyway, if you do apply a pier blockage, it's not necessarily a bad thing because you'd have slightly conservative results. Now, there's a little link down the bottom there for those who want a much more lengthy description on all that. So let's look at this case study. So this is the velocity field, and these are TUFLOW classic results from 2011. So you can see the strong flow of water in the middle of the river. You can see the piers there. In this simulation, there's no piers, so it's just sort of nice and smooth. Let's see what happens if you block the whole cells out, because it's very quick and easy to do that. You get some nice sort of wakes behind the piers. Yeah, we'll have a look at whether that gives good result or not there. If you just do a standard hydrology bridge waterways analysis on that structure, it's a bridge in China, you come up with a KP of about 0.14. That's your flow constriction, 0.073. So let's apply that across the whole waterway. Basically, hydrologically rich waterways is for 1D modeling. So you must apply that loss across the whole waterway. And if we do that, the presence of piers, so yes, we don't really see the effect of the piers in here. So in fact, it's almost impossible to tell that you actually have applied that 0.14. Very hard to tell any difference, but we'll have a look at the profiles at the end. If we actually add the pier blockage to the model, once again, applied across the whole waterway, you can just see there's a slightly darker red through there where that pier blockage is applied, and that's giving, but it is applied across the whole waterway. So it gives you a line of slightly higher velocities. The other approach is to actually apply form losses just to the pier cells. And what we've found is if you take this approach, it works quite well. So down here, we'll just focus on this pier here. We're going to say that the red line is basically the contribution it makes to the waterway. So we can individually calculate a J value for just that red section based on that pier. That comes in here. We end up with a KP of around about 0.32. Then what you can do is, because we're going to apply that to 2 cells, and this red line represents 10 cells, you can factor up that 0.32 by a factor of 5, 10 on 2, and you get a value of 1.6. So we apply a KP of 1.6 to that pier. And so the results are quite nice in a way. So you see a wake forming with that higher KP value on those cells. And what's really nice about this approach is that you can assess the individual effects of piers rather than the whole waterway. Let's add some blockage. If you add the pier blockage to that simulation, you just see a stronger wake behind. You actually even start seeing surcharging in front of the piers because there's a blockages applied to those cells. And yeah, so that also gives quite nice looking results. So how do all these results compare together? Well, the answer comes out from using hydrologically rich waterways is around 29 millimeters. These are results from Classic and TUFLOW HPC, which we ran yesterday. Had to find the old model. And you'll see basically these middle 3 all give pretty good results. You can see that the dashed red line is the hydraulically rich waterways, and they're all sitting on top of each other. If you block the whole cells out, you get very different results. And the last one, which was where we blocked the pier cells for the factored up KP, also gives probably too high a result. So very interesting outcome there. Okay, I'm just going to quickly go through some bridge decks before I wrap up. So what's happening in the bridge deck modelling world is that, and some of you would have heard this, Queensland Department of Transport and Main Roads and ourselves have been doing an investigation on and off as sort of we find the time. And basically, the objective is to improve bridge deck representation in flood models and ultimately lead to more confident modelling of bridges in 2D models. And we're going to do that through, we're going to get some measured data, as I explained, do some CFD modelling, which has been happening, and some TUFLOW modelling. I'd just like to thank Urs from Transport and Main Roads for these slides, because he'll be presenting those at the TMR Tech Forum on February 2022. So I just grabbed a few of those slides with his permission. And so what Main Roads have been doing is doing lots of CFD modelling of different standard deck arrangements. And what we're finding is, so this is water rising through the deck here. So it's all relative to the underside of the deck. This is your form loss coefficient in terms of the afflux, form loss coefficient based on the structure velocity. So you can see here that the peak energy loss actually occurs around about, based on the CFD modeling, about 50% of the deck depth above the deck. So as you would expect, the energy loss increases and increases, but it keeps increasing to about this point. And then the deck becomes submerged and the effect of the deck sort of dissipates in terms of its contribution to energy loss. So what we've been doing in TUFLOW is to try and replicate that sort of shape, which is sort of coming out fairly consistently amongst the CFD modeling with, you have to sort of rotate your head and sideways and stuff. But this is to replicate that sort of similar sort of shape there. You can adjust how this moves and set this inflection point here as well. So we're sort of been exploring ways of trying to model that, that sort of CFD results in a 2D sense. We're also building in, as I mentioned, a 3D layer blockage and form drag feature into TUFLOW FV, our 3D model. So yeah, we're really hoping to, well, getting quite interested to see what results are going to come out of that. We're sort of doing that as I speak. The ultimate aim is really to get improved representation for pressure flow and submergence based on sort of some sound modeling, CFD modeling, but we're also, main roads have installed these gauges either side of this bridge. So you can see the bridge there, the gauges in. The models have been set up for that bridge site. So TUFLOW model, Flow 3D CFD model, and an open phone CFD modeling. And we've only had one flood event on that bridge site. Hopefully this summer we'll get a lot more. It's not wishing on having floods, but we'd love to have some decent floods at this bridge site. And so here's some early results. So this is just comparing the upstream gauge and the downstream gauge. If there's no efflux, that is the dashed line, pretty much. The yellow dots are from the one flood event that they've measured. It just got to the top of the bridge deck. You can see the bridge deck in the background here. This is the bridge deck, and here are the rails. So you can see as the water starts to hit the bridge deck, there's energy loss being lost, and the upstream water level starts to increase above the downstream water level. So there's various results there. The orange line is Flow 3D, open foam is in here somewhere. There's a lot of blue lines there, which are the different TUFLOW methods. And what's been interesting is that we did a calibration of the Iowa, one of the bridges in Iowa on the Iowa River, and with our new method, and came out with some parameters for each of the different methods we're exploring. And then we applied those exact same parameters to Gordon Bridge, and they really came in quite nicely, giving a nice result. So that's very encouraging. So situation at the moment is, yeah, looking good. Okay, time to wrap up before I run out of time. Okay, conclusions, constrictions. As I've discussed, 2D models will contract and expand the flow lines. So they're implicitly modeling the form losses. But you have to make sure you're using software which is using the complete version of the 2D equations, but the 2D will model those form losses due to change in streamlines. But not all the losses are represented. Coarse meshes will struggle. There's the 3D losses and sub-cell fine scale losses, such as a bridge pier. You need to be able to add minor form losses, and that there's probably more guidance needs to be provided in that space. Just be a bit careful. Not all schemes are the same. So, you know, if your scheme's a first order scheme, it will be numerically diffusive, and that tends to cause an overprediction of losses, which can be fine, but you just need to make sure you benchmark and have a feel for that. And if you link 1D structures into 2D, yeah, that can be a bit of a challenge in terms of what losses to apply to or remove from the 1D element to compensate for the 2D losses downstream. But hopefully our 2D approach to partial velocity automatic adjustment will overcome most of that uncertainty. Piers, if you can make a mesh fine enough, and particularly a flexible mesh will be the strong preference. You can produce a representation of the efflux. Once again, you need a good 2D scheme. If you've got a fixed grid and you've got subgrid sampling, that will also help quite a lot for that type of 2D model. You do need a good subcell turbulence scheme for modeling the wakes, and you may need to explore the subscreen cell turbulence parameter to do that. If your piers are sort of subcell or just across a couple of cells, your mesh is not going to be fine enough to do the first stop points there. You really need to apply form losses, and there's two different ways of doing it. You can just do the whole waterway using something like the hydraulically bridged waterways KP approach. And alternatively, you can factor up your KP and apply it pier by pier, which will give you probably more flexibility in terms of assessing different piers. And finally, DEX, I think we'll get some really nice guidelines coming out of this TMR TUFLOW investigation. They're aiming to have that in the public domain middle of next year. Yeah, so that will hopefully remove some of the uncertainty around modelling bridge decks. And look, finally, as always, benchmark, cross-check, understand your results. And there's a little thing I just can't, it's just one thing you take away from this webinar. It's so easy just to do a V-squared and 2G cross-check. Look at the head drop across your structure, look at the velocity, work out how much of a V-squared and 2G has been lost. If you're losing like 2 or 3 V-squares and 2G, something is wrong, something is not right. So typically most structures will be losing somewhere from a small amount of V-squared and 2G to maybe a really constrictive structure might be 1 or 1.5 V-squared and 2G. Yeah, so do that test. And thank you.
Bill, what an awesome presentation. You said I'd be a believer after I'd seen it. Well, I am. I said to Bill before we started this webinar in the practice sessions and the preparation, there's so many people here, you know, why do they all come? Well, pretty obvious now. The real world examples people love, if I can say that on behalf of everybody, and the graphics are just awesome. Technical stuff is all in there and you can read it in the book as well. But thanks so much for summing that up, Bill. Well, let's have 5 or 10 minutes of questions. I'm going to hand right over to one of Bill's colleagues, Chris Huxley, and his 2 colleagues, Phil Ryan and Shuang Gao, to chair the next, should we say 10 minutes, Chris? What do you think?
Yeah, I think 10 minutes should be good. We've already gone for an hour. So
we have. Thanks for sticking with us, everybody. I noticed some had to leave. Appreciate that you've got limited times, but I'm handing right over to Chris now, and Shuang and Phil when he can join us also. That'd be great. Thank you.
Thank you, Trevor. Yeah, thanks everyone for typing all the questions. There was lots there, so, up around 30 questions. And whilst answering those, I've been keeping a list aside of ones I thought people might be interested in hearing the answer to, and also a few curly ones that I couldn't answer. I'll start with just some interesting ones. Bill, someone did ask a question, and I'll join 2 together here. The question is, in TUFLOW, would it be better to model culverts in 1D embedded in a 2D scheme, or as a 2D flow constriction, assuming the cell size is suitable? So if there's enough cells, should you be using 2D or
yeah,
reverting back to 1D?
My preference would be to use, if you've got 2, well, maybe 3 or 4 cells across the structure, my strong preference would probably be to use 2D, a full 2D solution. If your structure is less than a cell size, it's better to probably insert a 1D element. The really grey space, really difficult space, and we saw that in those results I presented, is when you've got like 1, 2, maybe 3 cells across the structure. And that's where you'll have to fiddle with the losses. But the next version of TUFLOW will hopefully have this 2D approach departure velocity adjustment finalized, and that will really help clarifying or removing uncertainty around that grey space.
Mm-hmm. There actually was a few questions around that feature, Bill, and I think Rudy was mentioning that the sample location where you put that velocity information, it will influence obviously how it's treated. And Phil mentioned that there will be a sample location feature included in a future release. Yeah, so that's what we're trying to work out. What's the easiest way? I mean, you can try and automate it where you go upstream, downstream automatically, but then obviously nothing's in a straight line like that test example. So we might have a couple of options, one which is sort of automated, or the other option is you can just digitize that sort of line and snap it to your 1D structure. And it just takes the velocity profile across there and adjusts according to that. Mm-hmm. Yeah, so we'll as usual give lots of options probably because there's never a perfect answer. And Phil and Shuang like coding, so yeah. Keep them busy. When using a 2D approach, what is the lower limit of grid size you could or should use with an engine like TUFLOW? I understand that just lowering the cell size will not account for additional subgrid losses that typically occur at fine scale. So I guess, yeah, what's the lower limit of the grid size that you'd recommend?
Oh, well, these days with HVC and the Wu turbulence and other features, there's no real limit. I mean, we're seeing, like you're seeing that in that model there, the Shrung's been running, and big thanks to Shrung, by the way, for this, a lot of the modeling in this presentation. We're down to like tiny cell sizes, and it's more about the ratio of the cell size to the depth. And these days, with our latest features, you can actually pretty well go down to as small as you like, but without any constraints. Certainly in the TUFLOW Classic and with the older turbulence models we've had, you have to be careful of having a depth greater than your cell size.
That makes me feel good, because that's the answer that I gave. I did give a caveat as well, though, that like practically the simulation speed will probably be an influence. When you go down to really small cell sizes, the diffusion control number can ratchet down your time step. So
yeah, your run times can really go through, and that is to do with that turbulence term really kicking in and controlling a time step if you're using HVC. Yeah.
Mm-hmm. Any thoughts on best practices for modelling heavily skewed bridges with multiple piers, with the piers either in line with flow direction versus in line perpendicular to the roadway?
Yeah, look, I think if you've got a really complex bridge structure, you really may need to do some near field modeling, like a flexible mesh model, possibly a high resolution HPC model. So just to have a really good look at what the losses and flow patterns are, and what you potentially can derive from that near field modeling is basically a head loss versus height arrangement from that structure, which you then might be able to model in a more coarser system. So yeah, I mean, actually where we're taking the TUFLOW software is that we're setting it up so that you'll be able to embed a high resolution TUFLOW FV mesh inside, say, a HPC coarser mesh for far field. So you'll be able to build in like a high resolution structure inside your flexible, as a flexible mesh, 2D or 3D, inside your HPC model. So that's pretty exciting space that we're seeing in the future. Not yet though.
You did cover this question in your presentation, but it's good just to circle back and just reiterate the concepts. Someone asked, why are 2D form losses generally lower than 1D?
Because the 2D equations are modeling that change in form. So 2D is all about, if the water suddenly changes direction left or right, there's a loss associated with that. And the 2D equations just automatically compute that loss implicitly inside the equation. So whereas 1D has no concept of left or right, it is just unidirectional. So 1D you have to explicitly put in your full form loss, whereas 2D will model most of that form losses without even having to think about it. But as I said in the presentation, there are some form losses in that really fine scale subcell, or in the vertical, you might get helicoidal circulations around a river bend is a good example. We had that on the Brisbane River, where 2D won't model all the form losses. So you just have to top it up a bit, typically, with that. And there's some really good calibration work coming out of the studies, such as Brisbane River flood study on that.
Right, so it captures it in the horizontal, but in the vertical,
exactly, yeah. Yeah, and anything that's subcell, so anything that's obviously below the resolution of the mesh.
Okay, this one relates to a specific TUFLOW feature. It's asking about layered flow constrictions. What's the difference between the pier blockage and the form loss value? What is the impact of adopting a higher pier blockage value versus a low value?
Yeah, so pier blockage simply just adjusts the flow area. So if you put in a 50% pier blockage on that cell, that will reduce the flow area of the cell faces by 50%. And what that will do, it'll push the water sideways, and then that creates you're also constricting the flow by doing that. So you generate higher velocity. So you'll get a better representation of the velocity through the structure. The tricky space is the form loss coefficient, which is representing the subcell losses, such as the wake behind the pier. That often the KP value from hydrological bridge waterways is not based on on the structure. It's not based on the velocity with the pier blockage included. So you may possibly need to dampen down that KP value a bit if you really want to be precise. Although I would also argue it doesn't hurt to be a bit conservative in these modeling of these structures, because there's always uncertainties, and sometimes it's good to be a little bit on the high side.
Right. There was a few questions about the vena contractor in the 1D. I'll ask them one after the other. So regarding the 1D approach and the entry of water constricting, if we have a long flume, and is there a method for determining when the water will get back to uniform flow? Like, is there some sort of magic ratio or?
Well, it will depend on the configuration of the entrance structure. So if you have a square edged, it'll form a pretty hard vena contractor. As in a very tight one, you'll get a big circulation. So it'll take longer for it to reform inside the structure. If you have rounded entrances or wing walls or anything that smooths the water inside the structure, then of course the vena contractor will be much, well, the actual flow width will be bigger, but in the vena contractor eddies will be much smaller. So it'll reform much quicker inside the structure. And so then in the ultimate case, of course, is the minimum energy weir or structure. There's a few of those built around here in Brisbane. So what that does is it just transitions the water very gradually into the constriction, then it expands it very slowly. So you have very little energy loss associated with that type of structure. So that's the other extreme. So yeah, and that's why you'll see lots of QDM has got quite a nice discussion around that, and why you'll see different entrance coefficients for structures based on their entrance configuration.
Right. Okay. Well, you started answering the follow-up question, which was, do you have any guidance on vena contractor in particular, where you can get the coefficient values that go into TUFLOW? Yeah,
look, I think that's pretty straightforward, whether it's certainly from a 1D structure point of view, and is just take whatever value, say, QDM has for that sort of entrance configuration. So typically, square edge is around 0.5, but a wing wall or a rounded entrance might be 0.2 or 0.3 entrance coefficient. So just type that in. And that value will be adjusted by the approach velocity automatically in 1D. And in future, the 2D approach velocity will be also adjusting that.
Okay.
Chris, we've hit the 11-minute over mark, and we're getting a few people ready to sign off, but how would you want to approach this?
Like, I might just ask one more. I haven't seen what questions have been asked since I left the stream, so I might actually pass it over to Syme. We've got a separate chat, and he mentioned that David had a question that might be interesting. Syme, can you take the mic and ask that question?
Oh, sorry, I was just typing vigorously in the Q&A panel. David have a question saying what we presented was to model the pier wake turbulence almost explicitly with very fine mesh, but that's obviously not a practical method in the real world application. So he's asking if we have done any benchmarking on that one, and what's the guidance to estimate the foam loss in this case, when I think the mesh size is relatively coarse and you have to model it in subgrid foam loss. Bill, do you want to?
Oh, yeah. So sorry. So the approach, if your mesh is getting that coarse, you really have to move to a form loss applied to the cells approach. I mean, if you've got data, you probably start with whatever the hydraulically rich waterways will come up with. And so far, what we tend to see is we always get a good match with that. But then you are trusting the hydraulically rich waterways KP curves as being representative. So you simply have to move to that, apply a form loss approach. And if you want to do it individually, peer by peer, you can do that factoring up approach, which I explained at the end of the peer presentation section.
Mm-hmm. All right, let's leave it there, Trevor.
Right, then we should move to a to a full online course here. I can see this is a way more than you can handle in 1 hour. So, but thanks so much everybody for your participation. Appreciate the questions, the discussion. It's been absolutely wonderful. There's a recording coming your way. It's uploaded to the website and we'll give you the link to that. And also there's a short 1-minute survey which is going to pop up. It will help us shape these future webinars. And you can see here what's going on here. It's no wonder Joel is never home, or he doesn't stop, that's for sure. And Renee, thank you so much for your support today, Joel and Renee. And this is the reason these Australian Water School staff are flat out. I won't go through them all. You can see them, on-demand courses, webinars and live courses. Pick one and you will be greatly benefited. We'll leave it right there. I think there's no more to be added unless you've got any last comments, gentlemen. And
I was just going to say a huge thank you to you guys. You really you make our life so much easier doing.
Well, it's something I personally love. I know Joel does, and Renee's come on board now, and it's been a fantastic way to do professional development training. It just means you don't have to get on planes, you don't have to worry about COVID, you don't have to worry about anything, just jump online. It's fantastic. Your time and availability here across Australia, mostly up the east coast of Australia, has been fantastic.
I do want to know though, are you now converted to this topic?
I'm pretty converted, I tell you. I'm pretty close to it. I'll have another drink of not water. I'll have to have another drink of tawny port, and I'll probably get converted because it's going to take the numbers kill me. That's the problem. The numbers are just shocking.
Well, you can rewatch it tonight when you go to bed. That'll put you to sleep.
I like your sense of humour. Thanks so much, Bill, for your time on this, and Chris and Chuang and Phil and all your colleagues there at TUFLOW. It's been absolutely great. We look forward to another one to do this together. It'll be absolutely wonderful. Thank you for joining us, everybody. We'll sign off now. Bye for now.
Trevor. Thanks all.
Yep.
Bye, everyone.
See you soon.
Thanks, Trevor.
Bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.